We've talked about diffraction through a slit, but something that's usually more useful to us and is a little bit different is diffraction through a circular hole or aperture. When light goes through a small hole, it spreads out in all directions. If we didn't have diffraction and we had a light like this in some sort of sheet, the intensity profile would look like this. It would be well lit here and absolutely nothing outside of this, kind of like a perfect spotlight. What it actually looks like is more like this, where it's bright in the center, it gets dim as you move away, dark here, gets bright again. We can look at this profile a little better here. If you've seen this super slow motion video of a drop of water or milk hitting a surface of liquid, it kind of looks like that. This is that cross section, and it shows that we get bright spots, dark spots, bright spots again. The reason this is important is this tells us whether we're looking at one source of light or two. We need to know this for a few things. For example, if we have a spy satellite or even a mapping satellite, we need to know its resolving power. How well can it determine what we're looking at on the ground? In astronomy, we need to know, are we looking at one star or more than one star? And while human twins are fairly rare, about 30% of the stars you see when you look up in the sky are really double star systems. And this is much more important than it sounds. We have no way to find the mass of a planet or star or asteroid or even Earth except by using Kepler's third law and looking at the period and orbital radius of something that orbits it. If we're looking at other stars, we in general can't see their planets. Until maybe 20, 25 years ago, we couldn't detect these planets at all. And there's only a very small number compared to the number of stars that we can detect. So what we have to use is these double star or triple star systems where you can see both of them and they're moving around each other. If you ever take a course in stellar astronomy, which is usually the second semester astronomy, practically everything we know about the life cycle of stars and how they form and how far away they are can be traced back to finding their masses with this method. What we're looking at is how do we determine whether we have two stars or one star? It depends on the telescope's ability to resolve them, and we don't want something subjective like one person looking through it and claims they can see two stars while another person looks through the telescope and says, I only see one. We need something more objective, and what's become a pretty much universally agreed upon criteria is that if the maximum of one star's light profile is closer than the other star's first minimum, we'll only see one star. If they're more separated than that, we'll see two. So you can imagine, here's what we're talking about with the intensity profiles. If the peak of one is closer to this other one than its first minimum, we won't be able to see that we have two stars. And here we have something, obviously this is a blob, we can't tell that there's a second star there at all. Here we have two stars that are pretty well separated. It's pretty clear that there are two sources there. Here we're sort of on that dividing line where it's not very clear what's going on. So what we needed to do when we were looking at diffraction through a slit was find the zeros of sine of theta equals m lambda over d, or for the first minimum it would just be sine theta equals lambda over d. We know that we get those zeros when theta equals pi or some integer multiple of it, so it's pretty easy to find this. We had a very easy formula to find the minima for single slit. On the other hand, these functions, these Bessel functions, we have to find the minimum of the first Bessel function, and that happens at x equals 5.14. The function we need is 2 pi divided by that, or about 1.22. That's really background you don't necessarily need, but if you're wondering where this weird factor of 1.22 comes from, that's it. Theta is always going to be a small angle because we wouldn't be asking ourselves if we're looking at two things close together or one thing if they were far apart. We can use the small angle approximation. Instead of saying sine of theta is 1.22 lambda over d, we can just say theta itself is 1.22 lambda over d. The theta that we find here we can consider to be the resolving power of the instrument, and in some books you'll see this represented by capital R. In this case, we want the smallest number we can possibly have because that means two things can be closer and closer together, angularly speaking, and we can still see them both. This is only a function of the size of the aperture and the wavelength used, and we can use this technique to estimate the resolving power of your eye. For lambda, you can see a whole bunch of wavelengths, but we picked the middle of the visible region at 550 nanometers. D would be the diameter of your pupil. If we're talking about stars, then we're talking about the diameter of your pupil at night, which is about 7 millimeters. That would give us 0.0000959 radians. If we want to put that in degrees, we multiply by 180 over pi, and we get 0.0055 degrees. That's still small, so we can introduce the idea of arc minutes. There are 60 arc minutes in a degree, so if we multiply this by 60, we get 0.33 arc minutes. We could go further and write this in arc seconds. There's 60 arc seconds in an arc minute, and we'd get about 20 arc seconds. In reality, you can't really get this level of resolving power with your eye because the atmosphere is so blurry and fuzzy, it distorts things too much. This problem with the atmosphere is the reason space telescopes are so important. If you put the Hubble on the ground, it wouldn't be in the list of the top 40 largest optical telescopes, and it wouldn't have been the largest telescope in the world 100 years ago. The thing that makes it so special is it's out in space. It can achieve its diffraction limited resolution, which you won't find on earthbound telescopes. If we use the same wavelength of light and with the fact that its main mirror is 2.4 meters in diameter, and we put it in degrees and then arc minutes and then arc seconds, we get about 0.06 arc seconds. This is incredibly good. This is much better than even the high altitude large observatories in Hawaii. The best spy satellites, in fact, are supposed to be basically telescopes like the Hubble pointed at the ground. We can ask ourselves what they can see on the ground. They orbit at about 400 kilometers out of altitude. If we go back to radians, we can write the Hubble or the spy satellite's resolving power as about 2.8 times 10 to the negative 7, and we can try and figure out what can they see on the ground. Well, we need to know what's the separation of 2 points if they're 400 kilometers from the observer, and they have the angle here, 2.8 times 10 to the negative 7 radians, between them. Ordinarily, we'd use the tangent function. You can see the geometry here. If alpha is the angle, apparent angle between these two sources, d is the distance, x is the distance between the sources, we could do the arctangent of x over 2 divided by the distance, and that would give us this angle theta, and we would double it to get alpha. However, since we are talking about small angles, sine of theta and tangent of theta are both approximately equal to theta, so that simplifies this a whole lot, and we can just write theta is x divided by d. Now, if we plug in our resolving power for theta and our 400 kilometers for d, what x do we get? We get about 11 centimeters. This is not necessarily good enough to identify a person in particular by their face, but it's not far from it, and those satellites can actually go lower. We could get better results if we had shorter wavelengths and poorer results with longer wavelengths, but you have to keep in mind we don't often have that choice. For example, we can't look for people in the ultraviolet or the radio range because that's not what they emit. We have to look at whatever the object emitting is brightest at, whatever its peak wavelength is. That's the smart thing to look at. For example, radio telescopes look at completely different things than visible telescopes, and an individual radio telescope usually has horrible resolving power. The largest one in the world, and this is pretty new, is called the FAST telescope in China. It's 500 meters across. So if you think about that, that's more than 5 football fields. And the shortest wavelengths it can observe, which would give us the highest resolution, are about 0.1 meters. That would give us a resolving power of about 0.8 arc minutes. Remember, your eye is better than that, although, again, your eye can't see radio waves. Images from small radio telescopes kind of look like, if you look at the weather forecast and you see high and low pressure maps where you have these kind of blobs with an H or an L in the middle, the blobs are kind of like what you get out of these low resolution single telescopes. There is a trick, though, if we use something from the last chapter, and that's interferometry. If we combine the data streams from multiple telescopes, we can use interferometry to make a telescope that has the resolving power approximately equal to a single telescope with a diameter equal to the separation between the telescopes, which is called the baseline. That means we could put radio observatories on opposite sides of the Earth and have a telescope with a resolving power. It's been deleted here, but what this would be is 0.1 meters, 1.22 times 0.1 meter divided by the diameter of the Earth, which is 2 times 6378,000 meters. When you do that math, you get 0.002 arc seconds. Notice this is way better than the Hubble. It's a different frequency range, so it's not a direct comparison, but that's ridiculously high resolving power, and this is not limited by the atmosphere. Now, that's not really as good as a single telescope the size of the Earth, because the light gathering power, or the amount of radiation this thing can catch, does depend on the real physical size and not the baseline. The kind of question you might see on a test or homework, let's say you have an infrared telescope with a 40 centimeter aperture and you're looking at light of wavelength 1.75 microns. There are two IR sources 5 centimeters from each other and 10 kilometers from you. Can you see them as two sources, or will you just see a single blob? The first thing we do is find the resolving power of the telescope. Remember, that only depends on wavelength and diameter of the telescope's aperture. We get about 5.3 times 10 to the negative 6 radians. What's the angular separation of the two sources? It's 0.05 meters divided by 10,000 meters. This is 5 times 10 to the negative 6 radians. This is a little bit smaller than the resolving power of the telescope, so that means we can't quite see two. We just see one single blob.